So things are pretty similar with a telescope. What you want to do is produce an image, of course, that is an angular size of the image should be bigger than the angular size of the object that you're looking at with your naked eyes. So faraway objects, say the moon over here. When you look at it, will have an angular size. We just talked about that, which happens to be the same as the sun. So whatever angular size of the moon it is, that's how big it looks to you. That determines how much detail on the surface of the moon you can see by just looking at it. But the light rays that are coming from the moon are very much to be close to being parallel. That doesn't mean that this light ray and this light ray are parallel. What the condition that the object is far away means is that the light rays coming from one point of the object, by the time they make it through the eye, they must be moving, they must be very parallel to each other. When they diverge, of course, when they come out of the object, they're going in all sorts of different directions, of course, but the light rays that make it inside the eye, that make it through the pupil, they have to be coming at a very parallel. Right? If you were looking at these light rays coming from a point really far away, they look parallel here, but if you continue here thousands and thousands, hundreds of thousands of miles, then they would converge at a point on the moon. But if you look at it here, they look perfectly parallel. Okay? So parallel light rays, when they hit the eye, they get focused on the retina and without accommodation. Right? Those parallel light rays will hit the retina at some point here. Which point, or how do you know exactly what point, at what point they hit the retina? Well, those light rays are coming at an angle theta, right? And we do know that the light ray that hits the center of the retina, nothing happens to it. It just continues moving. So that light ray is going to continue that way and hit the retina. So we used this property before, that the image of an object and the object itself are located along this line defined by the light ray that goes through the center of the lens. So this angle over here is the same as this angle over here. Okay? The light ray is going all the way there. So notice that there is no issue here about, with your naked eye, if you could change the distance to the object, what would be the angular size of the object? Because you cannot change the distance to the moon. You change it by such a small amount that it doesn't matter at all. So the angular size of an object that is really far away, like the moon, that is a number, and that's determined, and that's the same for everybody, on Earth at least. Right? So what is a telescope? What do you want a telescope to do? Just as with the microscope, you want to form an image of the object that you're trying to look at. You want to form an image of that object at a point that is close to the focal point of the eyepiece. That's what you want to do, just like you did with a microscope. So the light rays coming from the moon that come in parallel. I'm going to show you this. It's going to take me a long time to draw that. So these are the light rays coming from the faraway object. As I said, they must be coming parallel to each other. That doesn't mean that the angle at which they're coming is going to be 0. Okay? The angle would be just the angular size of the object, a few degrees for the moon. And those light rays are coming in at this angle, and they're going to be focused at one point, because this is a convergent lens. That point would coincide, that point will be a distance equal to the focal length of the objective. This distance is the focal length of the objective because those light rays are parallel to each other. Okay? If that distance, if the location of the intermediate image coincides with the focal length of the eyepiece, then the light rays coming from this point, they will turn parallel on the other side. So a person looking at those light rays, first of all, doesn't need any accommodation to form an image of those light rays. So they seem to be coming from this direction. So the angular size of the object will be the angle determined by this, and you could say the line in the middle, or you could say, well, these light rays are coming from the top of the moon, there must be light rays coming from the bottom of the moon. Those light rays would have the same angle but going this way. They would hit the lens over here and be focused this way. So the overall angular size of the object would be, you say, 2 times this angle. It doesn't matter if you put a factor of 2 or not. The point is that the angular size is determined as before by this angle over here. And you want to compare that angle, see how much bigger is that angle, how many times is it bigger than the angle that you would get by just looking at it with your naked eye. That is what's called the theta of the objective, is this angle. The light rays from the moon are making an angle, a specific angle. So you compare those two quantities. The first one is h prime over the focal length of the eyepiece. Put a minus sign there because it's going to be inverted. The second quantity is the angle that the light rays coming from the moon make. So that's that angle, which is the same as this angle over here, which is h prime divided by this distance, which is the focal length of the objective. So h prime divided by the focal length of the objective. That's what's going to tell you the magnification. So h prime cancels above and below, and you get a ratio between the focal length of the objective and the focal length of the eyepiece. So now for a telescope as opposed to the microscope, the difference in the magnifying power of the two lenses is important. In other words, if you find a box in your house that has 2 lenses and they have the same focal length, you cannot make a telescope out of that. They have to be different. If there is a ratio between them, if this one is 2 times bigger than this one, if one of them is 2 times focal length bigger than the other one, then the big one will have to be the objective and the smaller one will have to be the eyepiece, and the ratio between those 2 focal lengths would tell you how much bigger is the image that you can get with that telescope. For a microscope, that's not an issue. With a microscope you can have 2 focal lengths that are the same and that still magnifies. It's just because of the setup being different. Of course, as I said, you want to make the focal length of the objective big to get bigger magnification. So a telescope has the end of the telescope, the one that is pointing at the stars, must have a big opening, typically, because the focal length, you want the focal length to be big. And the focal length, if you're using a lens, the focal length is related to the radius, right? To the radius of curvature. So if you want to have a big lens, big focal length, you need to have a big radius, right? So that's why a telescope would be so open on that side, and you want to have as small as possible focal length for the eyepiece. So that's why when you look at a telescope, you're looking through a small hole. But you cannot make this a lens gigantic, because then the weight of the glass is too much and it would bend. So what a professional telescope does is it does the same thing here, except that it does it instead of having instead of having a lens which is made of glass, it is actually a concave mirror that has converging power just as the lens does, and the setup looks a lot like that, and the magnification is the same. It's the ratio of the focal length of the objective, which could be a mirror, divided by the focal length of the eyepiece, which typically is not going to be a mirror.